Okay, so we are talking about the 12 big functions. The first one I want you to write down is, it's called y equals x, or f of x equals x, so write that down. And it is just a line. It's as simple as that. This line is the simplest of all functions. And if you're asked a few questions underneath it, like for instance its domain and range, that should be pretty easy. How far to the left do you think that thing would go if you just continued it forever? Negative infinity. To how far to the right would it go? Positive infinity. Is there any stops along the way? No, just continuous the whole time, right? Okay, so is it continuous? Yes. And its domain is negative infinity, positive infinity, and its range, how low does it go? Negative infinity. How high does it go? Positive infinity. Is there any stops along the way? No. All right. Now, the next one to the right of that, I want you to put down the greatest integer function. Now, this one is tricky. You tried it. You may not copy all of it, but you got to get the idea of what's happening here. F of x is like y, right? So it's like saying y is an integer, meaning y can't be a decimal, because integers are like whole numbers. So the integer function means that you can't have any decimals. It's only going to be like whole numbers and negative numbers, like -2, -3, but it has to jump and not go in between one number to the next. So as I move over a notch, it has to go up to the next whole number, but it won't ever go in between. So does something like this look continuous to you? No, because there's lots of gaps. All right, and I'll let you figure out on the domain and the range. I'm obviously not asking you to call out every little gap in it, because you'd be writing them down for the rest of your life. So figure out how you're going to say that. All right. I'm not going to answer all the questions. I'm going to just tell you what the functions look like. Here's the next two. F of x is x squared. You know that one. It's parabola. Don't just freehand it in there. Put in a few points that are important, like 1, 1, 2, 4. 3 squared is 9. Okay? And again, I think you can figure out things like, is it continuous or not? Well, continuous just means once you start drawing this thing, do you ever stop? Do you ever have to like jump over a gap, or it doesn't have any gaps or discontinuous spots? Okay, moving over to the logistic function. Don't try to answer every question, or I will go too fast for you. Graph the logistic one now. And it goes down to 0. There's an asymptote down here. I'd put a dotted line across there if I were you, so that you know there's an asymptote. And there's also an asymptote here on the top end of this one. This is a function I'm sure you have never seen before. And it comes in handy when you're talking about populations, because this is a function that's great for approximating a population. Let's say that you knew that this forest place in northern Minnesota could hold, let's say it's like 100 acres, it could hold a certain number of deer. I mean, think about it. You can't just have an unlimited number of deer live on your land, can you? I mean, once you get to a certain point, there'd be like deer stacked on top of other deer. There just wouldn't be room for all the deer. So there's got to be a limit somehow, even just on space. But if nothing else, there's a limit on food, because they got to eat stuff. If the deer get really, really hungry, they start eating your trees. It's true. They will eat trees to survive. Anyway, so if there's too many deer, a lot of times they end up starving, and then it brings the population back down to a level that the land can sustain. So this is a limited function. It's got a top. And in fact, if I said that there was a area that could hold 40 gerbils, but that's all the food there was going to be, was enough to handle 40 gerbils, then if the top number would be 40, and this would go to 40, and it would top out at 40. And then you can do stuff along the way to say, like, after how many weeks would it be maxed out or whatever. Okay, so that is an interesting one called the logistic function. That is not a log. Logs are different. This is the logistic function. It's related to logs. But. All right, next two are cubed and absolute value. I think you know both of them pretty well. One thing I would be surprised to find is how many kids didn't know how to put in absolute value on their calculator. I know you know how to put in x cubed on the calculator, but absolute value. So I'd like you to grab your graphing calculator and go to the y equals, and to get absolute value in there, it's under math. Go to the, first get on the y equals screen, then go to math. And then go to number. The arrow over. If you need to borrow one of mine, please do. Don't just sit there. I need you to be typing this in to your calculator. I have more if we need more. Okay. So absolute value, and I hit enter. And by the way, if yours doesn't have little bars, if yours says ABS on it, then yours is the old style operating system. So go back to your y equals screen, and when you've hit math, I'll show you where it was again. Math, arrow over to number, and number 1 is absolute value. If you don't have an absolute, oh wait a minute, now I got an absolute value of an absolute value. There we go. If you have a little ABS on your screen, raise your hand if yours says ABS. All right, you guys have the old operating system. If you want the new operating system, here's what you got to do. First of all, look at your calculator. If it's a TI-84 or newer than that, like an Inspire, then your calculator can handle the new operating system. Who still wants the new operating system? Because your calculator can handle it, like I know yours can. All right. You don't have to have the new operating system, but it's free, and I can give it to you as a download from my calculator. Okay? It'll be easy to do, and it's this operating system that basically just makes things go a little bit faster and has a little bit nicer print for things. So that's all you're missing out on if yours is an older calculator like an 83 or an 83 Plus. Actually, 83 Plus might be able to handle it because it has more memory. So we should try yours, see if it works. All right. So anyway, I can give you that operating system later if you want it. So I say absolute value of x, and I hit graph. And I don't know if you can see this, but do you see how my graph is better than the one on my worksheet? Because the one on the worksheet, do you see how it sort of looks squished a little bit? Do you know why it looks squished? Because if you're in a normal zoom, zoom 6 is standard zoom, it's squished. It's squished down. So if you want to see something on its true picture, and this is going to be a little bit like, I don't know, annoying probably for you, to realize that all the graphs you've been graphing up to this moment in your life have all been skewed. They've all been squished. Why? Because the numbering on the x-axis and the y-axis is different. Look at it. Look at the little marks. The difference on the y-axis, those are teeny tiny little ones. On the x-axis, they're about twice as wide. So all your graphs have been squished. So go to zoom square. Zoom number 5. Zoom square. Now that's the normal. That is where the tick marks are the equal length on the x and the y-axis. It's one of the great injustices of your life. You've been graphing these things all this time, and they've been always squished, and you never knew it. Okay, so this is an absolute value. They have 45-degree angles. I guess 1, 1, 2, 2, 3, 3, 4, 4 are all points that will be important, or negative 1, 1, negative 2, 2, etc. Okay, moving on. Next two functions we have are the reciprocal function. I know we've graphed that before. And that's the 1 over x one. Remember the two key points there are at 1, 1 right here, and at negative 1, negative 1 right there. And then after that, they just get closer and closer to the asymptotes that run here and here. All right. Now the cosine function, again, stretched. I would like to have your cosine function look like, I don't know, like it should, in my estimation. And so let's go to y equals, type in cosine, it's the cosine button, x, hit graph, and again, go to zoom 5 if you haven't already done that. Zoom 5 gives you your standard zoom, or sorry, not standard. It gives you your square zoom, meaning that the x and the y are the same size. And I can zoom in if I want to like see it a little bit better. Just hit zoom in, hit enter one more time once it's done, and then you'll actually zoom in. Now, if that feels like we're in too close, then zoom out, whatever works for you. But that's your cosine function. Basically goes up and down. The highest it ever goes is 1. The lowest it ever goes is -1. We'll learn all about that later. But for right now, it's just kind of generally how do these things look. All right. The cosine is the sort of like the parent function. For sine, sine looks, oh, I'm wrong. Sine is the parent one. Cosine is actually related to sine, but sine actually is like the parent. And you shift sine over and you get cosine. They're pretty much the same thing except shifted. All right, we're going to move on. Notice if you're picking, like cosine and sine look so much alike, try to remember how they interact with the origin. I'm going to cancel that. Okay. How they look with the origin. This one, on cosine, when it starts up high at 1. But sine, when it starts at 0. So anyway, yeah, that's how you can tell sine apart from cosine. Sine starts here, goes up, back down, then back up to, oh, where is it going to intersect this? I think I did that off a little bit, but basically sine starts going up. I'm going to just leave it at that. Okay, we'll show you that one in a second. So here's the next two. The square root function and the natural log. You know the square root one, things like 1, 1, 4 goes with 2, and 9 goes with 3. Now, natural log, ln, that's one that you probably never have graphed before, so I want you to actually see that one in action. Go to your graphing calculator. Go to the y equals, type in ln, which is way on the left here. I'll click on it so it turns red. There's the ln button of x. And then I hit graph. Mine's on zoom 5 again. This is the natural log. Now, in case you can't tell, that line, there is an asymptote line that's right here. It's going to never touch 0. But there is not an asymptote line here, like it seems like there might be. It does rise forever. Okay. All right, so this one will never be 0. So if you're doing the domain on this one, you'd say it starts at 0 but never is 0. How do you say that? 0 with a parenthesis. Good. All the way to infinity. That's the domain on that one. Okay, moving on. 2 more functions. Exponential function. You've heard of exponential growth, right? There it is. Exponential function is e to the x. E is a really special number I'm going to teach you all about later this year. It's about 2.7, and it's a number that's a lot like pi. You know, a pi is 3.14159265358979323. Anyway, E is 2.7 about. It does go on forever like pi does, but I don't have it memorized, so I just say it's about 2.7. It's another number that comes up in nature I'll share with you later. And then here's sine. Like a sketch of sine. Notice that again, sine, this one's been kind of stretched out. It's not so pointy when you graph it on a calculator that's got a square axes. Like you number the left, right, and the up, down the same way. It won't be so stretched. But anyway, sine starts at 0 and goes up from there. You're going to learn all about, that's one period of sine. You'll learn all about sine later on later in the semester. Yes? Is that even? Good question. So if I flip this left, right, can you see that it would look like that? That's what it should be if it was even. So it's not even. But if I flip it left, right, like I just did and made it red there, and then I flip it up, down, then it would match. Can you see that? Take the red one and flip it up, down, and it would look like that. Then it would match up. So what's a double flip? Odd. If you can do a double flip to get it, then it's an odd function. If you really understand this stuff, it all comes together. Sometimes it won't come together because you're not understanding it. That's okay. You'll eventually, hopefully, understand it. One more thing I want to point out. The e to the x and the ln x. Notice how these two, if I put them on the same graph, do you see how they're very similar to each other? In fact, they're an exact reflection over this line, which makes them inverses of each other. And that's something you'll learn. Just like we learned odd functions, even functions, you'll learn about inverses of functions. Those two are inverses of each other. The log and the exponential. And I want to go back up to the log one because I have just a dumb way to remember log. ln stands for log. It actually stands for natural log. And why don't they have the n first? I don't know. But doesn't this sort of look like a tree that used to be in the ground here and then got blown over in like a big windstorm and like blew over here? And what do you call a tree that has blown over in the windstorm and is now laying on the ground? A log. Ah. Okay. Because sometimes these things start to all blend in and start looking like each other. So that one I hope you can picture being a blown over tree. So it's a log. In fact, it's a natural log if you think about it. It's a tree. Okay, so you now know 12 functions. These 12 functions are the big ones. They're the ones that you need to know for the rest of this year and next year. Okay, they expect you to have these 12 functions memorized, just like we expect you to know what a square root, what a square root was. We knew that you'd know that from last year. And same with x squared. Well, you got a few more to add to your little list. All right. Now, tonight's homework is going to be the Algebra Ninja. So, I can stop my recording.